We know human civilization extends back about 12,000 years, but Earth itself is more than 4.5 billion years old. That leaves an almost unimaginable span of time. Billions of years in which something extraordinary could have risen and fallen before us, leaving faint or no traces behind. Recent 2025 sediment and seismic surveys, such as the discovery of massive buried sand mounds beneath the North Sea, show how new imaging continues to reveal hidden structures beneath the surface. If humans vanished today, most buildings and machines would collapse or corrode until unrecognizable within thousands to a few million years. What would remain are the chemical fingerprints, plastics, radionuclides, altered carbon, from which geologists might one day reconstruct our presence. We'll look at what modern geology and 2025 tools can and cannot reveal, and which chemical signatures might survive across vast timescales. This video will define the hypothesis, explore the durable clues geologists search for, examine the newest discoveries, and ask what those findings suggest about both forgotten pasts and our own future legacy. The core idea of the Silurian Hypothesis. The idea at the center of this discussion is the Silurian Hypothesis, a proposal born out of the scientific literature on astrobiology.
At its core, it does not claim that an earlier industrial civilization did exist, but instead asks a tightly defined question. If such a civilization had once arisen on Earth, would it still be detectable in the geological record millions of years later?
By framing the issue this way, the hypothesis treats civilizations not as isolated accidents, but as potential repeating phenomena within a planet's history. In fact, some researchers note that it reimagines part of the Drake equation, the formula used to estimate the number of intelligent civilizations in the universe, by considering that multiple epochs of industry could occur even on the same world. The result is less a speculation about lost empires and more a testable inquiry into what planetary scale industrial activity would leave behind after deep time has reshaped everything. A constraint immediately comes into view when geologists consider the mechanics of Earth itself. Because of erosion, subduction, and the recycling of the seafloor, direct archaeological evidence much older than a few million years is exceedingly unlikely to survive. Researchers point out that once you move beyond about 4 million years into the past, the chance of finding intact artifacts such as buildings, tools, or machines drops to almost zero.
This recognition sets a practical boundary for the discussion. Any search for evidence of earlier industry must rely less on physical remnants and more on indirect, chemical traces locked deep in sediments or preserved in isotope ratios.
From that perspective, a question emerges: what detectable planetary scale changes would any advanced industrial species leave behind? And could those changes persist long enough to be studied today? It is one thing to imagine earlier species building machines or cities, but the scientific challenge is more specific.
It is about identifying signatures distinct enough to separate industry from the host of natural forces shaping the planet. The Paleocene-Eocene thermal maximum (PETM) provides a caution here. Around 56 million years ago, the Earth underwent a sharp warming event marked by a dramatic release of carbon and a corresponding shift in isotope ratios.
To modernize, that spike resembles the chemical fingerprint of industrial carbon emissions. But the PETM was entirely natural, likely triggered by volcanic activity or the destabilization of methane hydrates. The resemblance to our own industrial signal shows how easily nature can mimic what we would expect from intelligent activity. This means that if we ever did detect an anomaly, one marker alone would not be convincing. Multiple independent lines of evidence are required to support any such claim. Thinking of our own species highlights the challenge further. Millions of years from now, anyone searching for traces of humanity would not find intact skyscrapers or highways. Concrete breaks down within thousands of years, steel rusts away, and even plastics only leave chemical residues rather than recognizably shaped artifacts. Fossilization itself is an uncommon event. Entire species can vanish from the record without leaving behind a single preserved skeleton. Scaled up, the odds of machines, infrastructure, or even bones surviving tens of millions of years are slim. This leads directly back to the point of the hypothesis. Instead of looking for recognizable remnants, the search must target signals embedded chemically in soil, rock, or ocean sediments. Examples of what counts as durable signals are increasingly clear in 2025. A layer enriched with byproducts of plastics, even after degradation, could still be recognized through unusual molecular fragments bonded in the sediments. Long-lived radionuclides created through artificial nuclear reactions could persist as faint signatures in certain layers of rock. And perhaps most robust of all, the redistribution of carbon and nitrogen isotopes created by large-scale fossil fuel burning or agriculture could leave traces that last for hundreds of thousands or even millions of years.
These signals would never appear as monuments or machines, but as subtle markers that a large-scale industry once rearranged planetary systems. Advances in technology have made this kind of search possible. A few decades ago, the best methods available could barely distinguish natural carbon fluctuations from industrial ones, and what little was known about human-made emissions was still being pieced together. Now, with high-resolution mass spectrometers and refined isotope analysis, measurements can be taken with astonishing sensitivity down to parts per billion. Entire archives of ocean cores drilled decades ago are being re-examined, this time with tools that can parse out details invisible in earlier studies. Sediment layers once cataloged as ordinary mineral deposits are being revisited, and in some cases scientists do identify small but striking anomalies that demand explanation. Machine learning tools now assist in identifying patterns in these chemical records, combing through vast amounts of data to flag unusual constellations of isotopes or compounds that could signal non-natural origins. The most important shift is conceptual. The Silurian hypothesis has moved beyond being a curiosity or a metaphor. It sets out a series of testable predictions. It asks whether chemical residues created by industrial activity, carbon imbalances, persistent radionuclides, synthetic molecules could remain detectable after vast spans of geological time. These questions are then tied to concrete analytic protocols, where every positive anomaly is followed by the challenge of separating natural from artificial causes. Events like the PET ensure caution, demonstrating that natural forces alone can produce signatures strikingly similar to our own impact. Only by looking for patterns across multiple independent markers can researchers avoid drawing false conclusions. This new focus also highlights an unresolved tension. Suppose future analysis of a sediment core were to reveal a sudden jump in carbon isotopes alongside unusual concentrations of heavy metals and long-lived radionuclides. Would that be enough to suggest an earlier advanced species, or could it still be the result of volcanic outpourings and asteroid collisions? Part of the difficulty is that geological catastrophes often distribute materials globally in ways not unlike human industry. The challenge for current researchers is to establish criteria clear enough to distinguish these cases even when the signals are faint and ambiguous. Even with these limitations, the Silurian hypothesis has achieved something significant. It shifted the conversation away from speculative storytelling and grounded it in the realities of geochemistry and planetary science. By doing so, the hypothesis transformed a question that once belonged to science fiction into a framework for interpreting the deep past of our own planet. That science remains cautious and probabilistic, but it stands as an example of using current knowledge to probe questions usually left to imagination. What remains uncertain is scale. Our own presence is so recent that we can still see highways, cities, and industrial waste with our eyes. But if the framework is correct, much of this would vanish quickly compared against the vastness of geological time. Which leads naturally to the question, if all physical traces fade so rapidly, how long does any evidence of us truly last? The fragile timeline of evidence.
The fragile timeline of evidence begins with recognizing just how quickly our most powerful creations disappear. A skyscraper or bridge feels permanent on a human scale, but without constant maintenance, these structures yield to decay within centuries. Concrete splits, steel rusts, glass shatters, and vegetation forces apart whatever remains. What once identified a city becomes, within a few thousand years, scattered debris almost indistinguishable from a natural rockslide. Against geological time, permanence collapses into brevity. Plastics may seem more durable, yet their resilience only shifts the form of their decay. Sunlight and saltwater fracture polymers, grinding them into countless microplastic shards. These fragments settle into sediment, no longer recognizable as objects, but leaving faint chemical residues. Even encased in rock, plastics do not preserve their original shapes. Instead, they leave behind distorted molecules, an invisible layer analyzed only with sensitive instruments. Machines and electronics fare even worse. Silicon chips, glass screens, and circuit boards crumble to dust within decades. In orbit, satellites eventually decay, burn in the atmosphere, or fragment until invisible. On the grand timeline of Earth, the era of technology would vanish with startling speed. Geology makes this disappearance even more certain. Wind, rivers, glaciers, and volcanic eruptions erase exposed surfaces relentlessly. Coastlines shift, mountain ranges rise and fall. Most decisively, the ocean floor renews itself. As continental plates dive into the mantle, sediments and even buried artifacts are dragged down, melted, and reabsorbed. Only in rare, isolated conditions can fragments escape. Fossils form under precise circumstances: rapid burial, low oxygen, minimal disturbance. Industrial traces would require similar luck, yet most would be eroded, scattered, or subducted before fossilization could even begin. Because Earth constantly remakes itself, studies have tried to estimate how long civilization's evidence might be measurable. Early conjectures suggested 10 million years might erase almost everything.
More refined models in recent research now give a sharper window. Most recognizable structures are effectively gone within 1 to 5 million years. Beyond that, the survival of buildings or machines is nearly impossible, though isotopic or chemical fingerprints could endure far longer in sediments not disturbed by tectonics.
In geological terms, our mark on the surface is shallow compared to the vastness of planetary cycles. The contrast with the fossil record of life highlights this fragility. Dinosaurs ruled Earth for more than 160 million years, yet they remained surface unevenly, often as partial skeletons or scattered footprints. Vast populations left only fragmentary evidence. If colossal organisms become scarce in stone, then a civilization existing for much shorter spans would fade even faster. What lasts is not architecture or machines, but shifts in chemistry, carbon isotope spikes, unusual metal signatures, or molecular residues strange enough to stand apart from natural baselines. Chemistry offers one more sliver of permanence. Some artificial isotopes created through nuclear activity possess half-lives stretching into tens of millions of years. Plutonium-244, with a half-life of about 80.8 million years, and Curium-247, lasting roughly 15 million years, would remain detectable if deposited widely enough. While none are presently known in ancient rocks, they illustrate the kind of unique markers that, if found, could confirm industry at planetary scale, even after eons. In contrast, less durable materials like copper wiring, plastics, and concrete vanish or transmute in far shorter intervals. These projections outline the narrowness of civilization's survival curve. At 1 million years, remnants become rare. By 5 million, the probability they persist declines to near zero, except for isolated isotopic anomalies or subtle chemical shifts in sediment. Stretch further into the timeline, and only those long-lived markers have even a chance of whispering that industry once existed. The difference between eras we can still study and epochs already erased is measured in layers of buried soil and centuries of tectonic movement. This brevity reframes both past possibilities and our own legacy. If another advanced species rose before humanity, its constructions would likely rest within the same fragile bracket, erased in a few million years, reduced to chemical peculiarities in stone. For our species, the lesson is the same. Skyscrapers, highways, and machines exist only as temporary monuments. What may survive deeper into time are thin strata showing altered carbon cycles, unusual concentrations of metals, or traces of synthetic molecules. Large-scale construction is fleeting, but chemistry can carry faint signatures far further. Recognizing this, the investigation cannot rest on artifacts. Those fade too soon. The realistic question becomes where subtle evidence hides, how to identify it, and how to distinguish it from natural processes capable of producing similar signals. That step turns attention away from ruined buildings and broken machines towards something else, the record beneath our feet, carried silently in stone. Searching the rocks for industrial clues. When the surface world fails to preserve, researchers turn to stone for the traces of change. Sediments and layered rock carry a chemical record of Earth's history, storing the remnants of atmosphere, climate, and catastrophic events over millions of years. If an industrial civilization once emerged before humanity, its presence would most likely survive not as buildings or machines, but as shifts locked into isotopes, metals, and molecular residues. The challenge is learning how to tell apart what only industry could create from what nature itself routinely imitates. Some markers rise above the rest.
Geologists now focus on 4 concrete proxies. First, stable carbon isotope excursions, delta TVIRS, delta 30C, which reveal abrupt shifts in the balance of carbon-12 and carbon-13, patterns that fossil fuel combustion leaves differently than volcanic outbursts. Second, nitrogen cycle shifts, delta 15, recording imbalances caused by artificial fertilizers rather than marine blooms alone.
Third, anomalous heavy metal ratios and distributions, lead, copper, cadmium, mercury, whose concentrations and transport patterns betray industrial activity more than regional eruptions. Fourth, persistent synthetic molecules and breakdown products, such as plastic fragments or halogenated organics, which have no direct natural counterparts.
Each of these signals can persist in sediments and provide testable, measurable evidence of disturbances beyond ordinary geology. Yet these markers exist against a backdrop of powerful natural mimics. Large igneous provinces, where tremendous volcanic outpourings cover continents, can overwhelm the climate and leave deep carbon isotope excursions.
Volcanic intrusions into organic-rich deposits can release carbon dioxide and methane in pulses that look industrial at first glance. Methane hydrate releases from the seafloor likewise generate sudden warming episodes, while asteroid impacts scatter rare metals like iridium and shock the climate in ways that ripple through isotopes. Events such as the Paleocene-Eocene thermal maximum or various oceanic anoxic events demonstrate how natural processes alone can leave signals that, if viewed in isolation, might be mistaken for technosignatures. This makes it essential to treat any one anomaly with caution. The real advance today lies not in single measure detections, but in multiproxy correlation. Researchers combine isotope geochemistry, trace metal mapping, organic molecule fingerprinting, and cross-site correlation to isolate anomalies that refuse to match known patterns from volcanism impacts or methane release. A lone carbon spike might be volcanic, but if it appears alongside industrial-type metal ratios and synthetic organics, stretched across multiple global sites, the case strengthens substantially. The guiding principle is simple. Industry spreads multiple kinds of chemical change at once, creating a web of linked markers. Keep listening. We'll show what geologists are actually scanning for. Carbon isotopes remain a primary proxy. Humans today have changed the balance of delta 30 by releasing vast amounts of light carbon from fossil fuels. The geological fingerprint is distinctive. Volcanic eruptions alter isotopes too. but in slightly different ways. The isotopic swing has its own character depending on the source carbon. Sediment cores sampled today are checked for ancient shifts of the same kind and with similar abrupt timing. A rapid global decline in delta A1-stained sediments would be a starting point, not proof in itself, but a flag to look closer. Nitrogen isotopes add a second dimension. Industrial fertilizers alter delta 1:15 ratios, leaving unusual imprints in soils and marine sediments. On regional scales, natural processes such as algal blooms can shift nitrogen isotopes, but global coordination and abrupt signatures hint at something larger. By assessing delta 15 anomalies across continents, scientists can distinguish between localized ecologies and planet-wide industry. If paired with a sharp delta 30C anomaly, the coincidence is far harder to dismiss as mere happenstance of nature. Metals contribute further evidence. Elevated mercury levels are often tied to volcanic events, but unusual combinations and concentration patterns matter. For instance, lead and copper clustering around certain layers could signal extraction and processing far beyond natural scatter. Researchers map vertical and lateral distributions of these metals across multiple drill cores. It is not the presence of a single element, but the ratio set alongside its spread that keeps the industrial hypothesis alive. Synthetic molecules provide perhaps the clearest distinction. Plastics, even as they decay, leave fragments of unique polymer residues. Modern tests show these fragments bond with sediments and withstand heat and pressure. Likewise, halogenated organics, chemical compounds useful in refrigeration and solvents, persist in ways no natural biochemistry generates. Laboratory simulations catalog how these substances transform under geological conditions. With that database, scientists scan older sediments for matches. A confirmed find would be difficult to explain without deliberate synthesis. Still, mimicry shadows each line of evidence. Ancient volcanic provinces, methane bursts, and asteroid shocks can create steep delta 1:130C declines. Intrusions of magma through carbon-rich deposits can mimic massive fossil carbon release. These natural paths complicate every readout.
For this reason, modern protocols insist on using multiple proxies together. One illustrative criterion researchers now cite is this: A.
Global abrupt delta 30C decline, paired with anomalous industrial-type metals and synthetic organics, would be far harder to explain by volcanism or impacts alone. It is not the signal, but the overlap of signals that matters. Methodologically, the process has grown sharper. Sediment drill cores only centimeters wide contain hundreds of thousands of years of chemical history. Advanced spectrometers now analyze with precision down to parts per billion. Each layer is logged against established baselines for known events, volcanic crises, asteroid impacts, methane releases, before deviations are considered significant. By 2025, artificial intelligence aids the search, scanning patterns that humans might miss. But interpretation remains a human task, balancing possible natural explanations against the hypothesis of industry. Progress also depends on international cooperation. No single drill site offers enough coverage. Samples from Asia, Africa, North America, and the ocean floor all feed into the comparison. With multiple sites, researchers can separate local oddities from true global signatures. If an anomaly repeats across continents, the chance of coincidence drops. Only then does the hypothesis advance from speculation to measured inference.
In the end, the rocks do not hold artifacts recognizable to the eye. Instead, they preserve needles of difference, isotope excursions, shifted nitrogen balances, clustered metals, or organic residues out of place. These subtleties are fragile in signal yet sturdy in endurance, capable of surviving millions of years.
The question remains whether those subtleties will ever converge into a pattern that nothing but industry can explain. And if there is any place on Earth where such a pattern might be preserved most faithfully, it is in the least disturbed archive of all: deep ocean sediments and the hidden archive. Beneath the world's oceans lies an archive different from anything preserved on land. The seafloor steadily gathers layer upon layer of fine particles, Dust carried by winds, microscopic shells from plankton, molecules from rainfall, traces of volcanic eruptions, even chemical byproducts drifting down from the atmosphere. While continents are scraped and recycled by weather, glaciers, and the motion of tectonic plates, many deep ocean basins accumulate record after record for millions of years. These sediments do not hold monuments or skeletons, but they preserve sequences of time pressed into thin layers that scientists can read with remarkable precision. Yet even this global reservoir has its limits. The crust of the oceans is younger than the continents. Because seafloor spreads from mid-ocean ridges and dives back into the mantle through subduction, few sediments older than about 170 million years survive. Any continuous archive of earlier ages before the Jurassic is gone. What remains of younger intervals is patchy, shaped by where basins escaped burial or tectonic disturbance. This makes every surviving core from the deep ocean precious. It is one of the few ways we can test not only natural upheavals in Earth's history, but also, in principle, whether signs of industry might once have been recorded and preserved. Accessing this archive has proven difficult on a practical scale. The seafloor covers more than 2/3 of Earth, but only a scattering of places have ever been drilled deeply enough to recover long sediment cores. Programs such as the Ocean Drilling Program and its successor, the International Ocean Discovery Program, have provided almost all of this material. Even so, these tubes of mud and stone, pulled up from thousands of meters below the surface, remain sparse compared to the immensity of the seafloor itself. The scale of the gap is sobering. Attempting to reconstruct global history from these cores is like trying to describe an entire desert by studying a few handfuls of sand collected from scattered spots. The sediments themselves also pose their own challenge. Each centimeter might represent centuries or even millennia of deposition. Within those thin layers, natural events make strong imprints: volcanic ash falls, abrupt shifts in climate, meteoritic debris. Detecting anything artificial requires identifying signals that are weaker, narrower, and easy to confuse with background variation. If a civilization before us changed the atmosphere with industry, its traces today would be faint, blurred by time, and folded into natural rhythms. Untangling that record demands tools that can separate subtle anomalies from overwhelming natural signals. Older methods limited what could be seen. Traditional analyses revealed broad events, vast injections of greenhouse gases, widespread volcanic activity, or extinctions. But they largely missed small-scale chemical disturbances, microscopic residues, rare isotope anomalies, or subtle clusters of metals could easily escape detection. For decades, the ocean floor remained like a vast book where only the boldest headlines could be read, leaving finer sentences invisible. That situation is shifting now. By 2025, international collaborations have increased the number of drilling expeditions and pushed into new regions. Deep cores are taken not only from well-studied basins, but also from neglected areas. New borehole technologies allow sampling at greater depths. The focus has begun to shift from isolated glimpses toward networks of sites where patterns can be traced across wide distances. Though the gaps between cores still span hundreds or thousands of kilometers, researchers are steadily creating a wider framework for comparison. One of the year's most striking examples emerged from 3D seismic imaging in the North Sea. Scientists uncovered immense subsurface sand structures, nicknamed synchites, hidden beneath the seabed. These vast buried mounds had never been recorded before, showing that even places thought to be well understood conceal unexpected landscapes. Such discoveries matter because they demonstrate how modern imaging reveals features invisible just a few decades ago. If geology can surprise us with structures of this scale, it is reasonable to think chemical studies with equally new tools may expose anomalies once dismissed as noise. Once cores arrive at laboratories, the analysis itself has entered a new era. Sediments are sliced thinly, and powerful spectrometers scan their chemistry at resolutions unheard of in the past. The output is immense, billions of data points too dense for humans alone to process. Artificial intelligence systems now help evaluate them, trained on the patterns modern industry creates. AI examines shifts in isotopes, distributions of heavy metals, and molecular traces, highlighting small deviations from expected background patterns. A single flagged anomaly is not proof, but the technology allows attention to focus where signals are most unusual. Already, these techniques have produced intriguing results. Some cores from the Pacific and Atlantic hold faint layers where carbon and oxygen isotope balances dip unexpectedly, in ways hard to reconcile with normal volcanism. Other cores contain unusual metal ratios that diverge from well-studied asteroid impacts. None of these individual finds overturns the consensus explanations, but they demonstrate that sediments can preserve patterns subtle enough to raise questions. And crucially, they show how 2025-era tools are pulling detail from records once considered too faint to examine. Of course, a lone anomaly cannot support the weight of extraordinary claims. The analogy offered by researchers is clear: a single disarticulated bone does not justify announcing a new species. The same is true for potential technosignatures. What matters is replication.
If unusual signals recur in multiple cores separated by vast distances, the case becomes harder to dismiss as coincidence. Cross-site correlation is not simply methodological caution, it is a necessity. Without evidence spanning oceans, no anomaly can rise above the level of local curiosity. That is why researchers do not expect to find skyscrapers or machinery. What they hope for are repeated chemical anomalies in distant sediments, because only a global signal could begin to make a convincing case. At the same time, this effort sharpens how we think about our own impact. We already know what the early layers of the Anthropocene look like. Plastics fragmenting into seafloor sediments, heavy metals accumulating from industrial runoff, nitrogen, and carbon isotopes shifting far outside normal background values. By defining the boundaries of our own industrial layer, scientists have a yardstick against which to measure ancient intervals. The sediments do not just record deep time. They also measure the ongoing experiments humanity conducts with each passing year. The significance of all this is not confined to the bottom of the oceans. While marine sediments provide some of the longest-lasting archives, they are not the only medium capable of capturing delicate traces. Other natural records exist that might, under the right conditions, preserve an atmospheric signature too faint for rock alone to hold. And there we turn to another storehouse of memory, one locked not in mud and stone, but in frozen water. The frozen records of ice cores. Ice cores provide a very different kind of archive, one that captures the atmosphere itself rather than just sediments or minerals. As snow accumulates year after year in places like Greenland and Antarctica, it compresses into ice, sealing countless air bubbles inside. Each bubble is a small sample of the air from the time it was trapped, preserving carbon dioxide, methane, dust, and traces of aerosol particles. These annual layers also allow precise dating. That combination, chronology plus preserved air, makes ice cores one of the most valuable tools for reconstructing Earth's recent climate and atmospheric chemistry. For the late Quaternary period, ice records are outstanding. They extend back hundreds of thousands of years and, in the deepest Antarctic cores, can reach a little beyond 1 million years. That window allows scientists to directly observe glacial cycles, abrupt warming events, and atmospheric transitions tied to natural shifts in the Earth's systems. But the limit is clear. Ice cannot offer continuous samples that extend into the tens of millions of years. Since hypothesized pre-human civilizations under the Silurian Hypothesis are suggested to have existed far deeper in time, ice alone cannot record them. Instead, its relevance lies in refining the methods we use to identify anthropogenic fingerprints and then translating those methods to older and more durable archives such as sediments and rocks. Understanding why the limit exists is straightforward. Ice sheets are not permanent features, they advance and retreat with climate cycles.
Pressure at the base of very old ice causes deformation, bubble stretching, and melting against the bedrock. That distortion eventually destroys the clarity of the atmospheric record. Even in stable places like East Antarctica, 1 million years is about as far as intact layers remain interpretable. Beyond that, anything once trapped in older ice has been obliterated by the flow and renewal of the ice sheet. This is why scientists treat ice as a recorder of the very recent geological past rather than the deep history of the planet.
Still, within that shorter span, ice cores make it possible to test what industrial-scale activity looks like when written directly into atmospheric chemistry. Humans have added billions of tons of carbon dioxide, raised methane levels far above natural ranges, altered stable carbon isotope ratios, and released novel
chemical compounds like chlorofluorocarbons and other long-lived pollutants. Many of these changes are now locked into the layers currently forming in Greenland and Antarctica. That gives researchers direct examples of what artificial climate modification looks like in frozen form. The catalog of these modern signals serves as a template.
Industrial fingerprints are not limited to gases. Aerosols from combustion change the composition of particles deposited on ice. Fertilizer use shifts atmospheric nitrogen compounds, leaving isotopic residues that differ from natural baselines.
Synthetic chemicals, though present in small amounts, are chemically stable and traceable at low concentrations with modern instruments. If anomalous fingerprints were detected in older ice layers, abrupt rises in carbon dioxide that coincide with non-volcanic aerosol residues, or nitrogen imbalances without clear biological explanation, they would immediately draw attention. Even though such signals can never extend back millions of years, this testing ground sharpens the distinction between natural and artificial markers. Advances by 2025 have changed what resolution is possible. Instruments now probe individual bubbles, not just bulk samples. This means scientists can measure atmospheric properties at near-annual precision, identifying sudden disturbances that might once have been blurred within longer averages. Machine learning aids interpretation, sorting through vast data sets to highlight deviations that require closer scrutiny. Already, some anomalies in trapped gases, spikes in methane, or unusual particle ratios, have been identified as natural rapid warming episodes or volcanic winters. But with these methods, if faint traces of industrial activity had occurred in the last million years, they would be easier to separate from background noise than ever before. Researchers are also exploring indirect extensions of the ice core record. While the ice itself cannot survive back tens of millions of years, gases released during its melting often enter other systems. Some isotopic imprints wash into marine sediments, while certain long-lived compounds may linger in soils or biomarker records far older than any intact ice. These redeposited signals do not provide the same precision as direct bubbles, but they can bridge the gap by linking atmospheric events with sediments that stretch deeper into history. It is not a substitute for ice, but it expands the reach of techniques first honed on frozen samples. The training role of ice cores is essential because they give a clean, datable archive of modern human influence. They allow scientists to refine their tools with known examples before applying those tools to much older, more ambiguous layers of stone. Ice shows exactly how anthropogenic activity looks when it is freshly written into the environment. Sediments and rocks then test whether anything similar, however faint, appears far deeper in time. Without ice, methods of interpretation would be far less anchored to concrete reference points. Importantly, researchers caution that anomalies in ice must be checked against known natural mechanisms.
Volcanic eruptions inject both carbon dioxide and sulfur. Asteroid impacts distribute distinctive dust and metals. If an anomaly appears without these accompanying markers, interpretation becomes more complex. This is where high-resolution cross-checks matter most.
The stronger the ability to pair signals carbon together with aerosol, nitrogen alongside particle content, the clearer the case becomes for separating natural from artificial causes. In practice, every newly measured anomaly must pass through this filter of comparison. Most can be explained by natural shifts once the data are fully understood. But the process itself adds value. It builds the catalog of what nature can and cannot mimic in atmospheric chemistry, sharpening expectations for what genuine technosignatures might look like. The existence of a repeatable framework for such interpretation that is the lasting contribution of working with ice. The promise and the limits are linked. Ice cores cannot reach far back enough to test the main premise of the Silurian Hypothesis directly. They will never hold atmospheric samples from 50 or 100 million years ago. But they do solidify methods, train instruments, and generate a living example of how a civilization reshapes air chemistry in ways that can persist. From there, attention shifts naturally to the more durable archives that can hold records across the vast ages, sediments that span entire geological eras, and chemical shifts bound into stone. It is here that scientists confront the grander question: what happens when the faint chemical record of everyday industry is overlain by catastrophic global events? Layers of ash, sudden carbon spikes, and abrupt extinctions reshape what is preserved. Those turning points in Earth's history become the next testing ground for weather. Technosignatures could survive at all, even under the weight of global catastrophe. Extinction events and vanished civilizations. Mass extinctions stand out as some of the sharpest boundaries in Earth's history, where flourishing ecosystems collapse, dominant species vanish, and entirely new orders of life begin to take hold. Each one leaves scars easy to spot in the geological record, dramatic gaps in the fossil record, sudden chemical shifts in sediments, and evidence of global stress. They are generally understood as the aftermath of vast natural forces, asteroid impacts, immense volcanic outpourings, or climate shifts that spiraled out of control. But the Silurian hypothesis raises a difficult possibility alongside these explanations. If an industrial civilization once existed, could its traces be buried within these same cataclysmic layers, obscured by catastrophe instead of standing apart?
The Paleocene-Eocene thermal maximum, about 55 million years ago, illustrates this difficulty with unusual clarity. During that interval, global temperatures rose rapidly by an estimated 5 to 7 degrees Celsius, and the geological record shows a more than 3 per thousand negative shift in delta 30C values.
The mainstream explanation attributes this to massive carbon releases from methane hydrates or magmatic intrusions into organic-rich basins. Yet the pattern looks strikingly similar to today's fossil fuel-driven changes: abrupt warming, altered carbon isotopes, and disruptions to ocean chemistry. For researchers, the PET serves as a benchmark, a reminder that natural processes can mimic chemical signals resembling industrial output. This raises the specific problem of the Silurian hypothesis addresses, identifying artificial fingerprints in records that already bear the marks of giant natural upheavals.
The overlap between catastrophe and civilization is doubly confounding, because mass extinctions do more than mark boundaries. They erase what came immediately before.
If an asteroid impact annihilated a society, its ruins would be buried under the planetary fallout, iridium-rich dust, soot, shocked minerals, while its chemical contributions would be blended into the dominant signal of disaster. Similarly, a massive volcanic flood basalt could coat continents with ash and inject gases for tens or hundreds of thousands of years, overwhelming any subtler geochemical signatures. In this way, extinction events are great erasers. They do not provide clean separate layers for species and civilization.
They merge the two, forcing any search for older industry to rely on teasing faint signals out of catastrophe's roar.
The Cretaceous-Paleogene extinction, 66 million years ago, is the example most people know. The sediments marking this boundary include a global iridium spike, clear evidence of an asteroid, and additional signatures such as soot, shocked quartz, and long-lived climate disruption. For most geologists, the conclusion is inescapable. An impact event eliminated the non-avian dinosaurs and reset life on Earth.
Yet under the lens of the Silurian hypothesis, the question becomes narrower. Are there smaller residual anomalies within these layers that do not perfectly align with an asteroid signal? If so, could those anomalies reflect contributions from processes other than impact, including the possibility of industry existing at the same time?
After tens of millions of years, any anthropogenic signature would be faint and hidden, but it would most likely lie buried under the overwhelming blanket of natural catastrophe. Runaway warming events provide further complication. Besides the PTM, other intervals show abrupt global changes in temperatures tied to large carbon inputs. The isotope records present sharp drops in Delta 30C together with major oceanic disruptions. These signatures look much like the chemical record being written today by fossil fuel use. The established natural explanations, volcanism, methane release, ocean feedbacks, satisfy most interpretations, but the resemblance to anthropogenic markers means the boundary between natural and potentially artificial becomes blurred. Without precise discrimination, the possibility, however small, remains unresolved.
This is where improved methods introduced by 2025 studies offer new traction. Isotope analysis can now separate narrower distributions in carbon signals. Carbon released from volcanic intrusions tends to have a broader isotopic variation, while fossil fuel carbon produces shifts much more tightly skewed toward lighter isotopes.
Applying this higher resolution to extinction layers has revealed cases where the signal does not perfectly align with volcanism alone. Such mismatches do not prove earlier civilizations, but they demonstrate how chemical differences might be used to test the question. Nitrogen provides an additional test. Today's industries, through fertilizer and combustion, transform the nitrogen cycle and leave distinct isotopic residue. Ancient sediments from extinction intervals sometimes show sharp nitrogen anomalies that go beyond what models for oxygen-depleted seas predict. Ocean anoxia can account for many shifts, but not always the extreme forms. Such results remain ambiguous, yet they teach researchers to refine what processes can and cannot create nitrogen spikes. This helps define whether unknown anomalies might require explanations beyond established natural cycles. Heavy metals complicate the picture as well. Large volcanic eruptions produce mercury surges. Asteroid impacts scatter iridium and platinum. But industrial-scale processes concentrate metals such as lead, copper, or cadmium in distinctive ratios. Careful mapping of extinction boundaries has revealed occasions when metals appear in combinations not fully congruent with known natural events. While caution is warranted, because geological variation is common, these uneven distributions capture scientists' attention, highlighting where closer analysis may be required.
Beyond isotopes and metals, researchers now suggest another line of inquiry based directly on the Silurian hypothesis: search for substances that nature does not easily replicate. These include persistent synthetic compounds, unusual isotope combinations, and especially long-lived artificial radionuclides. Elements like plutonium-244 and curium-247, if ever produced in sufficient quantities by nuclear technology, would linger through much of geological time. If their concentrations in extinction layers exceeded natural background from cosmogenic sources, that would be a powerful discriminant. Testing for such residues is difficult, but it provides one of the few truly decisive markers that industry could leave behind. The methodological response has shifted from speculation towards structured protocols. A credible claim cannot rest on a single anomaly. Multiproxy triangulation is necessary. Carbon isotopes must be matched with nitrogen patterns, both checked against metal distributions, with synthetic residues and radionuclides adding further weight.
Only when various markers converge can a suggestion be taken seriously. This multi-pronged approach is the safeguard against being misled by natural phenomena that mimic some, but not all signatures of industry. This perspective alters how extinction events are studied. They are not only crises that eliminated species, but also dense, noisy records where hidden signals might be buried.
Scientists working today accept that the odds of proving prior civilizations are low. Still, they recognize the importance of systematically ruling out every possibility, identifying what combinations of anomalies natural forces produce, and leaving open testing grounds where something else might be indicated.
Seen this way, the silence of extinction layers is not proof that nothing more is hidden there. It simply means that the dominant signals, the asteroid, the volcano, the climate feedback, drown out whatever else might exist. Discovering any true residual technosignature would depend on refining patterns until faint voices can be heard beneath louder ones.
From this problem arises a wider connection. The effort to detect possible signs of industry erased long ago on Earth mirrors another scientific frontier, one that peers outward rather than inward. When astronomers look for intelligence beyond Earth, they too search not for artifacts or ruins, but for chemical fingerprints and planetary signatures that stand apart from natural baselines. Astrobiology's hunt for technosignatures. When astronomers speak about technosignatures, they mean the measurable effects of technology on a planet. The focus is not on visible structures, but on indirect fingerprints, changes in chemistry, radiation, or energy balance that reveal activity beyond natural processes. Waste heat, industrial gases, and narrowband radio leakage are prime categories in the search for extraterrestrial intelligence.
Each of these has a parallel when the framework is turned toward Earth's geology. Waste heat corresponds to warming spikes in ancient climates, unusual industrial gases to traces of halogenated organics in ice or sediment, and long-lived radionuclides stand in for persistent radio evidence.
Linking these categories makes clear why the astronomer's toolkit can also apply to the geological record. Waste heat is among the simplest indicators. Any society consuming massive amounts of energy generates excess thermal output. From afar, an astronomer might notice a planet glowing faintly warmer than expected, its infrared emission exceeding the normal balance set by the star it orbits. Infrared surveys already scan exoplanets for such anomalies.
In Earth's terms, an ancient civilization might have left similar disturbances as abrupt warming episodes not easily explained by orbital variation or ordinary volcanism. That reasoning makes intervals like the Paleocene-Eocene thermal maximum compelling points of comparison.
The PET-IM's rapid greenhouse spike, while almost certainly natural, illustrates how waste heat signals could appear geologically, blurring the line between industry and natural catastrophe. Atmospheric chemistry provides another lens. Some gases are extraordinary technosignatures because they have no major natural sources. Anthropogenic halogenated compounds, the family that includes the CFCs phased out in recent decades, stand out here. Even at trace concentrations, they are powerful markers because volcanoes, oceans, and biology do not generate them in abundance. If astronomers ever detected such molecules on another world, it would suggest direct technological manufacture. That clarity is why geologists working on Earth's history pay close attention to ice cores and sediments for residues of similar compounds. Their presence in old layers would be hard to attribute to anything but deliberate industry.
Current analyses emphasize the need for caution, since contamination or localized anomalies could mimic such results, but the principle holds 9E fiston CFC-type residues carry unusual weight as potential technosignature analogs. Radio leakage functions differently.
Telecommunications here on Earth release radio signals that spill naturally into space, forming a temporary halo of electromagnetic noise. Astronomers monitor for narrow band signals, precisely because stars and planets rarely produce such focused frequencies. In geology, the analogy cannot be literal radio waves cannot persist as fossils, but the principle adapts. Nuclear power and weapons leave behind long-lived artificial isotopes. Some of these radionuclides have half-lives stretching into tens of millions of years.
Traces of plutonium-244 or curium-247 in ancient sediments, for example, if found in unexpected concentrations, would fill the role of a geological radio signal. They are unnatural, highly distinctive, and enduring, serving as durable proxies for technological presence. The difficulty running through all these categories is imitation by natural events. Just as distant astronomers must rule out volcanic activity before declaring excess methane artificial, geologists face overlapping signals in Earth's rocks. Volcanic provinces release torrents of carbon dioxide. Microbial ecosystems generate methane.
Impacts scatter rare metals. Unless anomalies line up across several independent indicators, the signals remain ambiguous. The lesson from astrobiology is methodological rigor. The same rule applied to distant planets applies here. No technosignature stands on its own. Each candidate must be checked against catalogs of known natural mechanisms and confirmed by multiple independent lines of evidence before remaining on the table. By 2025, initiatives that were once purely exoplanet-focused now extend their work inward. NASA, ESA, and global partners continue to model how technosignatures would appear in planetary spectra. Waste gases, thermal excess, and chemical imbalances are all candidate indicators. Those same definitions now shape geological research.
A sharp isotopic excursion in sediments must be examined the way an exoplanet anomaly would.
Could it be explained by volcanic outburst? Could orbital variations suffice? If not, what else remains? Artificial intelligence has accelerated this cross-fertilization. The algorithms developed to sift faint spectral data for signs of unusual
gases are now also applied to terrestrial archives. Ice cores, sediments, and marine deposits produce immense chemical datasets, ratios of carbon isotopes, traces of metals, concentrations of organics. The AI trained to differentiate human-made halocarbons from natural spectra can also flag suspicious layers where molecules or isotope patterns deviate from volcanic norms. What astronomers pioneered for exoplanets is now looping back into geology, sharpening both fields and ensuring that possible technosignatures are not overlooked. From interstellar distance, Earth today would look abnormal. Its carbon dioxide level exceeds expected baselines. Methane concentrations are anomalously high. Halocarbons appear in the atmosphere without large natural reservoirs. Waste heat in infrared matches the profile of industry. If other observers applied the very criteria we now use to assess exoplanets, our planet would qualify as a candidate civilization. That realization directs attention back through time. If another species ever altered Earth on a planetary scale, the anomalies would leave roughly the same chemical and thermal profiles behind. The technosignature framework already exists. The challenge is applying it rigorously to stone, ice, and sediments. Calibration underpins this approach. We already have concrete examples of how modern industry shifts atmospheric balances. Ice cores preserve the rise of carbon dioxide and the concurrent drop in delta-1-delta 13C from fossil carbon. Sediments capture nitrogen, cycle changes from fertilizer use. These signals form reference points. Without them, interpreting older anomalies would be guesswork.
With them, scientists can measure deviations in ancient archives against known techno-signature patterns.
This transforms exoplanetary logic into a tool for paleoclimatology and geochemistry, tying multiple disciplines into a single system. That integration also tempers expectations. Detecting techno-signatures in Earth's deep layers is not straightforward. Sediments compress, erode, or distort. Chemical records can be partial or noisy.
Traces of compounds degrade, metals move through groundwater, isotope baselines fluctuate. The framework borrowed from astrobiology provides strong criteria, but the implementation on Earth requires cautious, multi-dataset validation. Only convergence across independent indicators, carbon isotopes, nitrogen ratios, unusual metals, synthetic molecules, can begin to suggest artificial origin. Without that redundancy, anomalies remain more likely to belong to the realm of natural variation. The effort holds broad significance. For exoplanets, the search teaches us what civilization does to a planetary environment. For Earth, the same techniques test whether such traces have already appeared in our own past. Together, the work closes a loop. Each failure to confirm ancient techno-signatures sharpens detection abroad, and every improvement in planetary observation refines how we evaluate Earth's own record. In both places, the standard remains the same: rigor, replication, and careful discrimination between nature's voice and any voice that might lie beyond it. Applying those standards demands dealing with overwhelming quantities of data. Every sediment core, every slice of ice, every spectrum from a telescope adds to the archive. The anomalies we're studying are often subtle, buried within billions of points of ordinary variation. Recognizing such patterns requires tools far beyond what human eyes can parse unaided. And it is at precisely this scale that modern science has turned to a new kind of assistant, one capable of sorting immense datasets and flagging the hidden signals that may otherwise remain unseen. AI's role in decoding geological mysteries. Across the repositories of universities, drilling programs, and national surveys, the record of Earth's past is stored in cores, rocks, and frozen layers. These archives stretch across continents, but what they all share is density. Every centimeter of material pressed from the ground contains information spanning chemistry, mineral structures, isotopes, and organic fragments. This adds up to billions of preserved measurements. For much of history, scientists worked through these samples slowly, experiment by experiment.
But the scale of modern collections dwarfs the capacity of human analysis, and it raises a problem. If weak signatures of industry exist in these records, they may already be buried in the noise, waiting unnoticed among mountains of data. The difficulty is not only volume. Geological events overlap in appearance.
A flood basalt eruption leaves a carbon spike, heavy metal deposition, volcanic ash, and rapid warming. Industrial carbon emissions trigger similar chemical shifts. Sediments do not record motive, only chemistry. To distinguish one from the other means sifting for patterns so faint it can be easily overlooked. Outliers may sit hidden against a backdrop where volcanism and impacts already explain much of the variation. Without systematic triage, signals both extraordinary and fragile risk being missed. By 2025, the approach to this challenge has shifted through the use of artificial intelligence. In practice, AI acts as a triage system and pattern recognition tool. Its strength is not in drawing conclusions, but in combing through billions of measurements and flagging subtle deviations for human scientists to examine further. The training ground is the modern Anthropocene. Fossil fuel burning, fertilizer runoff, heavy metal extraction, and plastic residues have left chemical profiles across sediments, glaciers, and soils. These distinctive patterns are entered into supervised models so that when machines encounter truly ancient samples, they can rank whether the anomalies resemble anything produced by modern industry.
In this way, AI operates as a filter, organizing material and highlighting weak, scattered hints that might deserve closer human investigation. Two specific applications are already shaping how researchers work. The first is anomaly clustering. Systems evaluate whether unusual signals repeat across distant locations or align in time. A carbon isotope dip from a single site could be contamination, but if corresponding dips arise on several continents at the same depth, the anomaly is raised in importance. Linking anomalies geographically and temporally reduces the risk of chasing noise and lets scientists concentrate on layered signals that may stretch across the globe. The second application is supervised classification. Here, models directly trained on known industrial products, such as microplastic residues, nitrogen isotopes from fertilizer use, or heavy metal accumulation patterns, are used to compare older datasets. Instead of treating every anomaly equally, the machine ranks them by how well they match modern industrial fingerprints.
A high-ranking anomaly does not mean proof of civilization, but it does mean the signal passes through a coarse filter that mimics what existing human activity looks like when baked into geology. That ranking system helps prioritize limited time and resources for deeper geochemical testing. Modern spectrometry reinforces the role of these tools. Instruments now capture data at resolutions of parts per billion, returning chemical breakdowns with incredible precision. A single ice core layer may generate tens of thousands of readings. When scaled to thousands of cores or decades of collection, this growth in resolution quickly overwhelms human capacity to parse results. AI assistance is less about producing automated explanations than about keeping pace, preventing meaningful anomalies from being lost in routine variation. The sharper instruments become, the greater the need for systematic computational attention to distinguish true irregularities from ordinary background. Skepticism, however, remains essential. AI can detect patterns that are statistically unusual, yet entirely natural. An anomaly in metal ratios might be due to local volcanic variation rather than technology. Geological signals are inherently noisy, shaped by cycles of biology, water chemistry, and tectonics. For that reason, flagged irregularities cannot stand alone.
They must be vetted with traditional geochemical follow-ups and cross-disciplinary verification involving volcanology, climatology, and paleontology. The guiding principle is strict. AI helps prioritize, but human expertise decides, testing whether natural explanations suffice before considering anything extraordinary. Digitization has altered the infrastructure of research as well. Ice, sediment, and rock samples once isolated in separate institutions are now increasingly unified into central databases. This enables cross-comparison on a scale previously impossible.
An anomaly in a South Pacific sediment core can be quickly checked against signals of the same approximate age in Greenland or the Indian Ocean. What emerges as a multi-layered view, where faint markers can be compared across oceans and continents. Without computational systems to manage this integration, these broad checks would be logistically impossible. One outcome of this integration is renewed attention to cores collected decades ago, but long left unstudied. Many universities and geological surveys hold thousands of samples stored in basements or shelves. Under new AI-driven scanning methods, these archives are being reanalyzed.
Thin layers that once revealed only gross changes are now examined at far higher resolutions, creating digital records parsed through anomaly detection models. Some of these forgotten cores have already produced surprising signals, not definitive of industry but pointing to intervals in Earth's history that merit renewed attention.
This has made the low-hanging fruit of old archives a powerful part of current work, since the cost of reanalysis is low compared to fresh drilling expeditions. The cultural shift is notable. Scientists now think in terms of global pattern recognition rather than isolated case studies. Anomalies are treated not as single curiosities, but as test points requiring spatial and temporal replication. Multiple independent markers, carbon isotopes, nitrogen shifts, heavy metal ratios, and molecular residues must overlap before any anomaly is treated as meaningful. Framed this way, machines do not promise discovery on their own, but deliver the most efficient route to testing hypotheses that once seemed too speculative to pursue systematically. Results so far underscore both the promise and caution of the method. In some sediment sets studied again with modern tools, carbon isotope shifts aligned with unusual metal ratios, sparking debate about causes that go beyond standard explanations like volcanism. Yet nearly all findings remain open to natural interpretation once deeper testing is applied. This dual outcome, anomalies flagged quickly and then resolved cautiously, demonstrates the intended balance. AI is not a source of answers. It is a lens through which faint signals can be noticed and assessed with rigor by human analysis. The broader implication of this approach is accessibility.
For the first time, it is realistic to test hypotheses about lost civilizations through high-volume comparison rather than anecdote or speculation. Billions of data points, once inaccessible to manual inspection, can now be organized into patterns and made legible. Whether these patterns ultimately reveal anything beyond natural phenomena, the process itself strengthens the way archives are studied, ensuring that if such signals exist, they will no longer remain so easy to miss. Still, this does not change the fundamental question that continues to haunt the Silurian hypothesis. If AI and modern instruments can scan so broadly and so deeply, and if sediment cores, frozen records, and geological surveys have been examined at such fine scales, why has no unambiguous trace of prior industry been found? The tension between improved tools and continued absence sets the stage for the next challenge, the persistence of doubt even in the face of exhaustive searching. Why haven't we found anything conclusive? Skeptics often frame the challenge bluntly. If an earlier industrial civilization really existed, where are the artifacts? Human cities, roads, and satellites define our species at a glance, so their absence in Earth's deep record seems decisive. No carved blocks, no machinery, no engineered materials appear in strata older than us. The silence of recognizable artifacts is why critics dismiss the Silurian hypothesis as little more than a thought experiment. Yet the geological realities make this expectation misleading. Earth constantly reshapes its surface, and over millions of years, the odds of buildings, tools, or machines remaining intact fall to almost nothing. The first eraser is tectonics. Continents drift, collide, and split apart, with their outer layers recycled into the mantle. Ocean crust is younger still, never more than about 170 to 200 million years old before it disappears into subduction zones. Any settlement or infrastructure built along past shorelines, at the very places where human civilization now concentrates, would have long since sunk, melted, and vanished. Even massive structures would not resist this planetary recycling. Cambridge researchers reviewing the hypothesis concluded that for any civilization older than about 4 million years, the chance of finding direct artifacts becomes vanishingly small. That constraint reframes absence not as proof, but as the expected outcome of surface renewal over geologic time. Erosion is equally relentless. Wind, water, and ice dismantle whole mountain ranges, let alone human-scale constructions. A skyscraper left untended might collapse within centuries, spanning millions of years. Even carved monuments would be eroded into unremarkable rock. Sediment then buries what remains, compressing it into new stones stripped of recognizable form. Fossilization itself is rare. Only a tiny fraction of organisms survive as bones in rock. For cultural artifacts or technology, the odds are lower still. Metals corrode and return to or like minerals. Plastics fragment into microscopic residues. Concrete crumbles. What lingers is not architecture, but obscure chemical traces dispersed in sediments. Expecting stone tools or buildings from deep prehistory misreads how quickly the surface cleans itself.
Coastlines compound the problem. The majority of human infrastructure is built near oceans and rivers where food and trade resources are abundant. But coasts are geologically unstable. Sea level rise shifts boundaries inland, while glacial cycles later retreat them outward. Past cities along ancient beaches, harbors, or deltas would have been drowned, buried beneath marine sediment, or ground away by shifting waters, once consumed by these margins. The geological record preserves little beyond redistributed sand and mud. If an older civilization built with the same preference for coastal hubs, its traces would almost certainly have disappeared. Skeptics lean on these destructive processes to argue that the absence of artifacts invalidates the hypothesis. Yet the absence of statues or machines does not mean absence of evidence altogether. Researchers emphasize that chemistry endures far longer than form. Carbon isotope ratios and nitrogen imbalances, heavy metal concentrations, and even long-lived synthetic compounds preserve subtle anomalies in ways infrastructure never could.
This explains why geologists no longer search for objects in stone but for signatures in chemistry. The rock record is a chemical archive first, a library of forms only in rare cases.
In this framework, the focus is not on why we have never unearthed an ancient machine, but on whether odd chemical disturbances recorded in ocean cores or sedimentary layers could represent the shadow of technology. Another overlooked factor is the narrowness of what has been sampled.
Although Earth's crust contains billions of years of history, humans have analyzed only a minuscule fraction of it. Most sedimentary beds remain inaccessible underground, while many ocean basins have yet to be drilled. Field estimates suggest that less than 1% of Earth's ancient sediments have been examined in detail. This statistical gap cuts both ways. We cannot claim the geologic record is silent, because we have barely tested it. If evidence is rare, and the archive overwhelmingly vast, sampling bias alone explains why nothing conclusive has yet emerged. Until wider coverage is achieved, claims of uniqueness rest more on probability than certainty.
Practical barriers reinforce this limitation. Every deep-sea core requires costly expeditions, specialized ships, precision drilling, and years of lab analysis. Most surveys target climactic transitions, volcanic provinces, or petroleum reservoirs with commercial value. That leaves enormous regions bypassed, not because they lack relevance, but because funding and logistics demand selectivity. As a result, areas most likely to conceal traces of alternative histories may remain untouched. The absence of evidence is as much an artifact of where we search as of what may or may not be there. So why haven't we found anything conclusive? The core reasons are straightforward. Plate tectonics endlessly recycles the crust. Erosion grinds surface structures to dust. Fossilization preserves almost nothing outside narrow conditions. Coastlines bury settlements beneath ever-moving seas. On top of this, the searchable archive is immense, while only fragments of it have been penetrated. Cambridge's conclusion that artifact survival beyond a few million years is improbable underscores why failures to recover monuments or machines should be expected rather than puzzling. The archaeological silence may say less about whether advanced societies existed and more about the limits of what rock, ice, and sediment can preserve. What has emerged instead are chemical anomalies, subtle, ambiguous, and always in need of cautious interpretation. Researchers prioritize these not because they are the strongest evidence imaginable, but because they are the only evidence geology sustains over scales of millions of years. This reorients expectations. No matter how dramatic our skyscrapers may look today, the preservable residue will not be beams of steel, but altered isotope balances, redistributed metals, and faint synthetic molecules. To demand intact artifacts is to misunderstand both geology and time. Recognizing this, the silence of the record cannot serve as decisive proof of absence. Our own species, if erased tomorrow, would leave structural ruins for a geological blink of time. Within a few million years, only subtle chemical footprints would remain. If such faint signals could be overlooked in our own case, the expectation for prior civilizations must also be tempered. The lack of conclusiveness may be less mystery than inevitability under the rules of geology, and yet this understanding carries an unsettling mirror. If Earth so effectively wipes even industrial civilizations from its face, then whatever we leave behind may be reduced to the same ambiguous traces we now puzzle over. To consider why no clear evidence has been found is also to confront how fragile our own permanence is, and how quickly even our most enduring constructions may wash into silence. That realization sets the stage for a harder reflection, one that turns the question away from the past and asks what mark our own civilization will truly leave behind. Could we be next? Could we be next? The question does not imagine collapse for its own sake, but instead asks what of us would remain if our civilization faded and the Earth continued on without notice. From a geological standpoint, permanence does not arise from towering structures or vast networks of machines. It comes from the chemical shifts we have already imprinted on the planet. Plastics, radionuclides, and altered carbon cycles have entered the long record, embedding themselves into stone and ice in forms likely to outlast all monuments. Plastics are perhaps the most visible of these durable markers. Every discarded bag, bottle, or fiber fragments into smaller particles carried by wind, rivers, and ocean currents until they reach the seafloor or riverbeds, where they become part of sediment layers. Over time, these fragments blend with minerals and organic matter, hardening into formations now called plastiglomerates, mixtures of plastic melded with natural rock. Microplastics, even smaller pieces invisible to the eye, distribute globally and are measurable in sediment cores today. While their shape will eventually distort or vanish, their chemical residues persist and remain identifiable under analysis. If future researchers pierced through layers of hardened ocean floor, they would encounter horizons enriched with these synthetic markers, distinct from any process nature produces unaided. Equally significant are the radionuclides introduced by nuclear activity in the 20th century. Above-ground testing scattered isotopes such as cesium-137 and strontium-90 into the atmosphere, embedding them across the globe. Though those decay on relatively short timescales, other artificial isotopes like plutonium-239 with a half-life of over 24,000 years and even less frequent actinides endure considerably longer.
These materials became global markers of the atomic age, preserved in sediments and soils as a precise stratigraphic horizon. Unlike plastics that degrade into smaller forms, radionuclides leave quantifiable, timed sequences of decay.
Any geologist drilling 1,000,000 years hence could find these unnatural isotopes in stone and recognize that intelligent beings once built nuclear technologies, even if all physical infrastructure had long since vanished. Carbon dioxide remains humanity's most globally distributed trace. Since the Industrial Revolution, energy production has raised atmospheric concentrations far beyond those measured in the last 800,000 years of glacial and interglacial cycles. More telling than sheer concentration is the isotopic fingerprint known as the Suess effect, the distinct decline in delta-30C ratios caused by burning ancient fossil carbon. This isotopic decline is now embedded in tree rings, marine sediments, and polar ice. Unlike short-lived gases, isotope shifts remain measurable across vast spans of time.
They tell not only of altered chemistry but also of rate, because natural volcanic or orbital-driven changes unfold slowly, whereas human activity has created a steep, abrupt step change across less than 2 centuries. That timing is itself unusual enough to enter the geological record as a unique signal. Taken together, plastics, radionuclides, and altered carbon signatures form what stratigraphers already describe as an Anthropocene horizon. It is a marker likely to stand in sediments the way thin iridium-rich clay bands mark asteroid impacts or ash layers trace volcanic eruptions.
The presence of this boundary means we do not need speculation to ask whether traces of humanity will endure. They already have. Our durable signals are being laid down continually, forming a chemical horizon that future analysis will be able to distinguish from background variations of nature. Yet the nature of this record does not simply freeze present life as it is. Many of the durable signatures arise from materials or processes tied to crisis and overextension. Microplastics persist not as useful objects but refuse widely dispersed through ecosystems. Radionuclides highlight not daily energy needs alone, but also weapon tests and industrial accidents. Carbon dioxide levels, combined with isotope evidence, reveal intensification at a pace capable of disrupting climate and ecosystems. In all three cases, the record keepers that endure are precisely the ones tied to risks for stability. A future reader of these signals might see not images of flourishing but signs of imbalance written into the rocks. This perspective matters because it reframes collapse not as catastrophe foretold but as one possible path within geological time. If our cities and infrastructures decline, what would survive is not their form, but the horizon of waste and isotopes already laid down. Future researchers need not imagine deliberate communication to know we existed. They need only note that for a short epoch, strange polymers, artificial actinides, and rapid carbon disturbances appear before disappearing again. That is the mirror the hypothesis turns toward us. Civilizations may pass, but their chemical markers linger in silence. Even so, the story need not read as apocalyptic. The measure of permanence in geology is not about whether societies vanish, but whether their societies vanish but whether their signals merge with the archive of Earth. Ours already has.
This means whatever future unfolds, the Anthropocene horizon will remain as testimony.
Our architectures may vanish within millennia, but fragments of polymer, traces of isotopic imbalance, and atomic residues will persist as durable record keepers.
They offer an enduring chronicle independent of human memory, ensuring that if anyone someday reads the rocks, our presence will not be entirely erased. The parallel to earlier debates is unavoidable. Major warming events, such as the Paleocene-Eocene thermal maximum, still puzzle researchers.
Sudden delta 1 C&C drops greater than 3 per mil, coupled with warming of 5 to 7 degrees Celsius, resemble our current trajectory. Could future investigators mistake our Anthropocene spike for another PETM, attributing it only to volcanic activity or methane release? Just as we study the ambiguities of deep time, future geologists may face the ambiguity of our own layer. That raises the unsettling point. Our trace will be legible, but not always distinguishable without context. The boundary of the Anthropocene may register as simply one more anomaly on a long timeline of carbon disturbances. That is why current analysts stress interpretation. Multiple proxies must converge, plastics together with isotope shifts, radionuclides together with heavy metal anomalies, for our horizon to stand clearly apart. But even if interpretation blurs, the materials themselves will not vanish. Every microplastic woven into clay-rich silt, every actinide atom trapped within sediments, every carbon isotope ratio shifted downward, becomes part of the record, locked in place regardless of who comes next to study it. Could we be next, then, in the cycle of rise, imprint, and disappearance? On human timescales, it is unsettling. On geological timescales, it is predictable. Civilizations endure by maintaining balance with their environment. Those that overshoot leave records behind, but not continuity. Whether humanity adapts or fails, the Anthropocene horizon will remain, as irreversible and as measurable as an impact layer or a noxic event. What varies is only how much of our society continues alongside the record we have already left. So, when geologists in the far future dig through layers, what will they think when they find this patch of synthetic material and a sudden carbon spike? That's exactly the question we started this video with. The geological record shows that what endures are not monuments or machines, but chemical fingerprints, carbon isotope shifts, synthetic polymers, and long-lived radionuclides pressed into sediments. These become the only durable traces of our presence, forming an Anthropocene horizon that will outlast our cities. The Silurian Hypothesis places such questions within science, framing them as testable research rather than claims of hidden empires. Its value is in showing how careful analysis can distinguish natural upheaval from signals with no clear analog in known processes. We can search for lost civilizations, and in doing so, we learn what legacy our own will leave behind. Which ancient mystery should scientists revisit with 2025 tools? Share your thoughts in the comments, and subscribe if you want more explorations of planetary history and astrobiology. If you'd like, tell us which chemical markers interest you most, and we can dig deeper together.